Suppose that we have a triangle with side lengths A, B, and C, and angles alpha, beta, and gamma. Now let this point be the reflection of this point under symmetry with respect to this line. Then we know that this equals this, and that this angle is 90 degrees. We also know, because of the symmetry, that this length equals A, this length equals this length equals B, this angle equals this angle equals alpha, and this angle equals this angle equals beta. Also, this angle equals gamma. Now suppose I take the circle with center at this point and radius A. Then it would pass through this point and this point, since this equals A. Similarly, let's take the circle centered at this point with radius B, so it would pass through this point and this point, since this equals B. We get a situation like the one illustrated here. We have two circles, one with radius A and another with radius B, that intersect at 2 points, and the distance between the center of the circles is C. Since this length here is B and this length here is A, then A plus B covers the whole segment C and even more. And so A plus B must be strictly greater than C. This here is called the triangle inequality. It's true for any triangle that the sum of any two sides is greater than the third side. So it's also true that A plus C is greater than B, and that B plus C is greater than A. So if we have three sticks of lengths C prime, A prime, and B prime, such that C prime is greater than A prime plus B prime, then we can't construct a triangle from the three sticks. The lengths of A prime and B prime wouldn't suffice to cover the side C prime. And if C prime equals A prime plus B prime, then A prime and B prime would exactly cover the segment C prime, but again wouldn't suffice to create a triangle. Now let's return back to our triangle. All these triangles that you see here are the same as this triangle, meaning that they have the same elements, they have the same sides, and they have the same angles. Such triangles we call congruent triangles. So two triangles are congruent if they have the same sides and the same angles. And one of the main reasons why the congruent triangles are useful is that if we have two congruent triangles, then all their corresponding elements are equal. For example, if we draw the altitude to the side C in these triangles, then the lengths of these altitudes would all be the same, because the triangles are congruent. In other words, the triangles are the same, and so you can't distinguish one from the other. And so we must have that this length equals this length equals this length equals this length as well. What's more, the angle here equals the angle here equals the angle here equals the angle here. And we can do the same thing with the median, for example. The lengths of the medians are the same, and the angles that they make with the sides of the triangles are the same. And we can do the same thing for the angle bisectors in the triangles. They would all be the same lengths and give the same angles. The only condition is that all the elements that we draw are corresponding elements in the congruent triangles. For example, I can't expect that the length of the altitude to the side C in this triangle would be equal to the length of the altitude to the side B in this triangle. It just doesn't work. The two altitudes that we choose should be corresponding. If the altitude here is to the side C, then the altitude here should also be to the side C. And now, because these are congruent triangles, notice what I can do. I can take each triangle and put it on top of the original triangle, and they will match exactly. But now see what happens with this triangle. If I try to put it on top, it wouldn't fit. That's because it is a mirror reflection of the other triangle. See, if I put it like that, you're going to notice that this point and this point are mirror images of one another with respect to this line. And so this triangle must be congruent to this triangle. It still has the same sides and the same angles, but it can't fit exactly on top of the other triangle. Instead, it fits exactly on top of its mirror image. But that's okay. The two triangles still have the same sides and the same angles, so they're congruent. And the lengths of their corresponding medians, altitudes, or angle bisectors would still be the same. And now let's play a game. We have this triangle here with side lengths A, B, C, and angles alpha, beta, and gamma, and we have 5 candidate triangles. The goal of the game is to guess which of those triangles are necessarily congruent to the original triangle. For example, the first triangle has the same angles as the original triangle, and the side against the angle gamma is also the same. Then, is it necessarily congruent to this one? The relevant question to ask here is, does there exist a triangle that has the same characteristics of this one, but has different characteristics from this one? For example, the side length of this side is not B. Let's start with the base C, And let's construct rays that make angles alpha and beta with this side. Then, if we take the angle alpha here and beta here, we get this triangle. If we take angle beta here and alpha here, we get this triangle. If we take angle beta here and alpha here, we get this triangle. And if we take angle alpha here and beta here, we get this triangle. And now notice that this side of the picture is symmetric to this side of the picture under symmetry with respect to this side. Also, notice that this triangle and this triangle are symmetric to one another under a symmetry with respect to the perpendicular bisector of this side, which is right here. You can prove this by observing that this triangle is isosceles, and if we continue this line and this line intersect them here, then we get that this triangle is also isosceles, and so the two intersection points here and here lie on the perpendicular bisector of this side. Hence, all the four triangles in this picture are congruent. So, there is a unique triangle with the sides C and angles alpha, beta, and gamma, and therefore it must be congruent to this triangle, meaning that there doesn't exist a different triangle that possesses the characteristics C, alpha, beta, and gamma, but it doesn't possess the characteristics side A and side B. Now let's consider the second triangle, and let's start with the base C. At the base C, we must construct an angle alpha. For example, let's construct it here, and then select this point such that this length is B. But the angle alpha can also be chosen on this side, and then the point here would be such that this length is B, and then alpha could be chosen on this side, and this point here such that this length is B, and alpha could be chosen on this side such that this length here is B. Now notice that this line and this line are symmetric with respect to this line, and this point are symmetric with respect to this line. Similarly, this point and this point are symmetric with respect to this line. And so this part of the picture is symmetric to this part of the picture with respect to this line. Furthermore, with respect to the perpendicular bisector of the side C, we have that this triangle is symmetric to this triangle. First, you can notice that this line is symmetric to this line, and then from this equals this, it follows that this point is symmetric to this point. And therefore, all the four triangles in the picture are congruent, and therefore, the triangle that has side lengths C, B, and angle alpha between them is unique, and therefore it must possess all the characteristics of this triangle here, including the side A and the angles beta and gamma. Now let's consider the third triangle, and let's start with the base C. The third vertex is such that the distance to the first vertex is A, and the distance to the second vertex is B, or vice versa. So we construct a circle centered here with radius A, and circle centered here with radius B. The two intersection points of these circles are here and here, and the circles do have two intersection points because of the triangle inequality. We know that A plus B is greater than C. And the 2 points are symmetric to one another with respect to this line, because the circles themselves are symmetric with respect to this line, which happens to be their diameter. And so, this triangle must be symmetric to this triangle with respect to this line again, which means that the two triangles are congruent. Similarly, if we take the circle centered here with radius B and circle centered here with radius A, we get this point and this point, such that this triangle is congruent to this triangle. Now note that the two circles with radius B, the first centered here and the second centered here, are symmetric to one another with respect to the perpendicular bisector of the side C. And the same thing applies for the circles with radius A, the first one centered here and the second one centered here. They're again symmetric to one another with respect to the perpendicular bisector of the side C. This means that this point and this point, the intersection points of the two pairs of circles, are also symmetric to one another with respect to this perpendicular bisector, meaning that this triangle is congruent to this triangle. And hence, all the four triangles in this picture are congruent to one another, meaning that there exists a unique triangle with side lengths A, B, and C, which means that this here is this unique triangle, meaning that all these four triangles are congruent to this triangle. Now let's take a look at triangle 4. So I start with this base C, and then I construct this ray such that this angle is beta, and then I construct the circle centered here at this point with radius B. And I'm looking for the intersection point of this ray and this circle, because that's the point for which this length is B, this length is C, and this angle is beta. But look at this. The ray and the circle have two intersection points, which means that there exist two triangles that have a side length B, a side length C, and an angle beta against the side B. These are this triangle and this triangle. We know that this triangle is one of those triangles, but we don't know which one. We also don't know which one is this triangle. And so, for example, this triangle could be of this type, And this triangle could be of this type. So it's possible that this triangle and this triangle are not congruent, even though this side matches, and this angle matches. Now let's think about when this circle and this ray only have one intersection point. Well, that happens when this circle intersects this line at one point on the ray and one point on the other side of the ray. And when does this circle intersect this line on this side of the ray? Well, that happens when the radius B becomes larger than the side C. This is what happens in situation 5. We start with the side B, and then we construct this ray such that this angle is alpha. And then since this side is A, we construct the circle centered at this point with radius A. And we know that the third vertex of the triangle is the intersection point of this ray and this circle. And we can see that because A is greater than B, then the circle intersects this line at one point on this side of the ray and at another point which is on the other side of the ray. And therefore, there exists a unique triangle with these characteristics, meaning that it must be congruent to this one. Hence, we derived these 4 ways in which two triangles can be congruent. The first way is that if the two triangles have the same side length and all the angles of the two triangles are the same, such as in example 1. The second way is when the two triangles have two of their side lengths equal and the angle between them is also equal, such as in example 2. The third way is when the three side lengths of the two triangles are equal, such as in example 3. And the fourth way is when the two triangles share two of their side lengths, such as in this example, B and A, and the angle against the larger one of the two sides. For example, here, alpha is the angle against the side A, and the side A is larger than the side B, and therefore example 5 illustrates the number 4 here. In contrast, example 4 doesn't, because even though there are two sides and one angle that are shared between the two triangles, the angle lies against the shorter side of the two. Here's the optional problem. We have three squares next to one another, and we draw this line, and this line. We call this angle gamma, this angle beta, and this angle alpha, and we need to prove that alpha plus beta plus gamma is 90 degrees. And here's the solution. The first step of the solution is to construct 3 more squares as shown. Now let's construct this segment and this segment, and let's consider this triangle right here. Well, it is congruent to this triangle because they share this side equals to 2 units of the square, which equals this side, and this side, which equals 1 unit of the square, equals this side, and also this angle is 90 degrees, and this angle is 90 degrees. And so if this angle is beta, then this angle must also be beta. Similarly, this triangle is congruent to this triangle because they share this side 2 units of the square, this side 1 unit of the square, and this angle 90 degrees. And so if this angle is beta, then this angle must also be beta. Also, because of this triangle congruent to this triangle, we have that this side equals this side. And because of this triangle congruent to this triangle, we have that this side equals this side. Now we have that this angle is beta and this angle is 90 degrees, therefore this angle is 90 minus beta. But this angle is beta, and so their sum is 90 degrees, so this angle is 90 degrees. But now we have an isosceles triangle right here with an angle of 90 degrees. And so this angle must equal 45 degrees. And therefore alpha plus beta is 45 degrees. And from here it follows that we only need to prove that gamma is 45 degrees. But look at this triangle. It's an isosceles triangle because this side of the square equals this side of the square, and it has an angle 90 degrees, and therefore this angle equals 45 degrees as desired.